So I'm a bit of an oddity here. I don't make anything. I'm a user, basically. And I'm from academia, as you probably guessed, and what I do is gigahertz spectroscopy. Actually, spectroscopy is all the way up to terahertz of materials, and in particular, soft condensed matter materials. So I'm going to tell you a little bit about my world, which may give you some insights about how important it could be for your world, because this is actually a growing field. So let's hope this is working. I'll turn it on. Yeah. So let's start. Why bother, basically? I mean, what is it all about? Facetious, very much facetious, but not really the answer. And it all comes down to this equation, which says that the displacement field in any material, because of the application of an external electric field, is going to have this simple relationship to the external electric field, where epsilon is the dielectric permittivity. And for those who like a little bit of history, this, of course, is from Maxwell's equations, and James E. Clerk Maxwell was in the University of Cambridge just over there. So another way of looking at it is to say that basically there will be a further field developing inside the material, and that's the polarization field. What does that mean? All atoms, or other atoms, all molecules, let's talk about molecules, are really a collection of charged particles held together by forces. That means the charges will be positive and negative, and they will react differently and oppositely to whatever field you place upon them. That means that if I do place a field upon a bunch of these dipoles, they will do their best to align with that field. And that will then give me, inside the material, another field, the polarization field, marked up to here. Now, normally, the electrical strengths are such that this is dependent linearly on the same field itself. Now, obviously, it's not going to be as beautiful as my little picture here. Okay, because inside there will be internal forces and conditions applying. There'll be thermal energy, things will be moving. And what that really means is there's an awful lot of information about the material in here. So if we can access that, we have a nice window into what happens with those materials. Now, as it happens, it's quite easy to access that. That's the good thing about all of this. Okay, very easy, in fact. So, what can we get from it? Well, if you go to Wikipedia, you will find this rather simplistic picture of what the spectrum of the dielectric permittivity will look like if you do access it. Now, I'm using their picture because it has a very nice graphic on it which explains what's more or less happening. Basically, round about here, 100 gigahertz, there's a sort of boundary. Everything which is lower than that is because of collective motions, okay? The mass movement of charges inside our material. Everything above that is really because of the local motions inside molecules themselves, stretching of bonds, for instance, or if we get somewhere optical, the actual deformation of the molecule by the electrons moving out and moving in, okay? We're going to talk mainly on this area, which is really where I concentrate my work on. Okay, so what do we see? Well, let's go along. Well, first of all, let's have a quick idea of what polarizations we have. Everything is going to be classical, no quantum stuff here. If I look at a deformation of an atom, put a strong enough field, and then you're going to get a deformation of that atom. There'll be a separation of the centers of mass of negative charge and positive charge. I'll get a dipole. If I go lower and I get a molecule where there is already an inbuilt separation between positive charge and negative charge, and the classic example, of course, is water, the moment I stick a field on there, the positive wants to go one way, the negative wants to go another way, I will get orientations. If I then go even lower in frequency, and I come along and I look at ionic liquids, for instance, where ions, positive ions, negative ions are separated, they can move around freely. If I put a charge on there, they will also separate out. And I will get a polarization once again. In general, that is what we have. But of course, it's going to depend about what's happening inside that particular yellow area. What are the internal forces? What are the internal conditions? And that's what I want to find out about. So how can we do this? Now, how do we actually access that? It's quite simple. If you can measure the impedance, you can derive the permittivity of the material inside. Now, for most engineers, I know that for you the permittivity is some positive number and that's it. Not for me. It is a complex number, okay, because it relates to the loss of energy inside that material, i.e. the action of the field on the material itself. Now, there's various configurations you can measure impedance. If you're working up to 10 megahertz, you can just do it as a simple capacitor. In which case, this C0, which is a geometric capacitance, it's basically a form factor, if you like, will allow you to be simply calculated, and you can get, just from the impedance directly, the permittivity. Now, I am making one assumption here, and that is, of course, that the wavelength of the field that I'm using is much longer than the dimensions of the sample cell and the materials that I'm testing. This is called the lumped element approximation, and if you have that, then this is perfectly valid. And if I go slightly up, I can do this in a cylindrical capacitance as well, in which case that's the form factor that I need. B is the outer radius, A is the inner radius. I could do it in terms of a microstrip, very useful if you want to look at fluids flowing, and in which case that's the form factor. You have to basically measure it, calculate it, okay? And eventually at higher frequencies, I can even look at the fringing field on an open-ended coaxial probe, and that will work all the way up to about 10 gigahertz, and that will be the form factor that I would have to use. So easy to get. Now, I'm not going to go too deeply into measurement techniques, but let's just have a quick look at this one. That's a capacitor cell, okay, and you can see that there's an element which is happening outside the cell as well. It's a sort of like, if you want, a fringing field on the outside part of it. There's a sample I really want to measure. This was designed for a flow-through technique, okay, and if I then convert that to an electrical model, that's what the electrical model would look like, okay, and I can see I've got certain areas that I've got to take in consideration where this inductive element, this admittance element, they would actually be accounting for the actual lines, if you like, the measurement line that I'm actually using. So you've got to take those into consideration too. Now, I'll just plug a little bit this book. If you want to know a little bit more about the techniques and the details of how you extract the dielectric permittivity, you can always go to this lovely, wonderful book, where it just so happens I have a few chapters. Okay, so I mentioned that you have to calibrate out the effects of the line itself. Why? Because, well, what machines are we using? We're using LC meters, sorry. We're using VNAs. These are wonderfully great machines, fantastically calibrated up to their ports. Then you've got a line coming out to wherever your sample cell is, and you have to take out the effect of that line. But this is actually quite simple to do, and I like this. I stole this from the manual of LRC meters from Keysight, beautifully explained. And it shows you quite simply, if that's your sample, there will be the sample. If this would be stray inductive elements and resistive elements inside the sample cell, and this would be your line, then with a few specific measurements, yeah, you can actually calibrate those out. And basically you need to measure a short circuit, an open circuit, and a known load, and you can get whatever you want. So the techniques are very well developed, very nicely developed, I must admit. So, easy to do. What do we have? Okay, so this up to about 1 megahertz. This is a typical system. Nowadays, people doing dielectric spectroscopy find that there's only really one company we can talk to who can provide us with turnkey solutions. That's Nova Control of Germany. There used to be Soliton here in the UK. There's a few other companies, Zurich Instruments, also coming up now, offering useful solutions. But here's a challenge maybe for the audience. So basically, very simple. That really is an impedance analyzer just about there. The rest of this is all to do with maintaining the temperature of the sample. And this sort of system will measure from liquid nitrogen temperatures, 90 degrees Kelvin, all the way up to, in some versions, up to about 400 degrees centigrade. So it's a wide range. Now, that means I'm changing the thermodynamic state of the sample, whatever sample I've stuck inside there. A lot happens, and that's what I like to investigate. That's what I can investigate. We'll have a few examples along the way about what you can see there. You can also now get variations where they will change the pressure. So you can now do these sort of techniques up to gigapascal pressures as well. Highly interesting things happen. Very important when we're looking at polymers, for instance. You can also use them when you imply very strong electrical fields inside them as well. If you want to do aging experiments, take your polymer, for instance, and pass it through a series of strong electric fields over one day. It is the equivalent of leaving it out in the sun for a couple of years. See if your polymer is going to last. It's a very useful thing to do. Another way, here now we're up a little higher frequency, so we're using a vector network analyzer. I'm sure you'll all recognize the field fox. And here we're simply passing it down the line, and now we have to look at the reflection coefficient. If it's a lumped element approximation, this is still very simple to get out of, and it's still the same basic equation which relates the permittivity to the impedance that you measure. This is a cylindrical sample cell. We talked about that a little bit earlier. This is for the temperature control system that we would give it as well. We could go further. We could use an open-ended coaxial probe. Lovely little experiment we'll talk about a little bit later. That's blood. I get to investigate some really interesting things. I hasten to add, I didn't take it from a student. Although I can think of a student or two I'd like to, but that's not allowed nowadays. So. But here we're using an open-ended coaxial probe, a well-calibrated open-ended coaxial probe. That just so happens that in the 1950s some amazing work was done theoretically to relate the admittance at the end of the probe to the permittivity of the material it was sitting inside. Basically, you'll recognize that as the fringing capacitance. That's that piece there. The rest of this accounts for an antenna-like radiation inside your material, the losses from there as well. And that works very well. By the way, Keysight, that produces the probe, thinks nobody knows that equation. We found the original paper on which they based their software, so it was very interesting. And of course, you can use optical techniques. Now, you're going to use optical techniques when you start to go to higher frequencies, and suddenly you can't use lumped element approximations so easily. So this is, for instance, this is work done investigating, you can't see it very well, but there's a bit of very dark plastic there in the middle. And we're looking at the transmission through it because we want to get an idea of its absorption. Because we want to use it for electromagnetic shielding. Basically, so what are you doing here? Very, very simple. You're simply sending out a wave. We're collimating it. We are focusing it. Now, of course, that focusing is only going to be to a spot about one wavelength or two wavelengths in diameter, so you are limited. If I was to do this technique, this technique we did from about 25 gigahertz and above. If I was to do that technique in the megahertz region, the lens required is basically my height. So it's a little impractical and a little difficult to do. But it can be done. So you do this, you pass it through, and what you have here is that the calculated transmission coefficient that you get is really the ratio between the transmission coefficient of your sample, the transmission coefficient with no sample, and a factor to account for the thickness of your sample as well. Do that, and you can relate that to the complex index of refraction of the material itself. If the losses aren't too great, then you can even separate out this very, very simply into an extinction factor and the index of refraction itself. Here's an example. Those are the plastics. So that would be the free line, that black line up there. And as they added inside these particular plastics, we're talking PP, PA, polyamides. As they added inside there, it was carbon nanotubes. You can see that the absorption becomes greater and greater and greater until eventually you get to a concentration of nanotubes that this material can work as a very effective EMF shielding. Very good for cars, the electric cars nowadays, because you can mold this stuff unlike metal, doesn't add to the weight. So that's one application that's coming along. So this is all the techniques that we have. So earlier we talked, and I said that the dielectric permittivity, we can get it. So what does dielectric permittivity look like? If you remember a long time ago when I first started talking, there was a picture, okay, of the spectrum. So here's the spectrum for water. Now, how do we describe that spectrum? Because, you know, you need to make something which is useful. You can talk about numbers that characterize what you're looking at, okay? Well, in this particular case, you can use something called the Dept function. The Dept function, it's a complex function, as you see. Its real component will fit that, and its imaginary component will fit this. It was first invented by Peter Dept all the way back in the 1920s when he introduced this concept of the molecular dipole, that there will be molecules have the separation of charge inside. And it is a nice, easy function, and it's one of the few functions you can really derive from ab initio, from first principles. You have a dipole, you have a field, it will do the following. Great! Unfortunately, nature is like a rather badly behaved 5-year-old child. Never does what it's supposed to do. And in fact, a lot of the times you find this. So you'll see that now it's gone down in amplitude and it's broadened out, it's smeared out. It's actually quite symmetrical, but smeared out. And in fact, the equation needed to describe that is this one, the Cole function, first introduced in 1941 by an American physicist, a couple of brothers actually, Kenneth Cole and Bob Cole. Now, if this could be characterized by two parameters, the strength and the relaxation time, i.e. where that peak sits on the spectrum, this needs three parameters to describe it, where this alpha describes how it broadens out. We're going to talk about that a little bit because I'm a physicist and I can't help myself. I have to throw in physics. This is the DC conductivity, okay, and it appears in both of them, and we'll talk a little bit about that as well. Now, there are other functions, but we won't talk about these. These are simply more complex. We'll concentrate only on these two. So let's look at what actually happens. So one way you can change situations, especially in water, is dump stuff inside. Now, this is rather important because almost all water that we encounter in nature has stuff inside it. It's almost never pure. Specifically, the water inside us, we are 70% water, and in particular, the blood inside us has an awful lot of stuff inside it. This will be ions, potassium, calcium, sodium. This will be residues of amino acids, all sorts of other junk inside there, and of course, proteins and cells bumping around inside. We would love to know a little bit more about what goes on inside because that's how we can understand what's going on inside ourselves. So, what actually does happen? Well, we'll notice that if you stick in ions, that pure water peak, if you measure it, and we're measuring there in the frequency region from about 10 megahertz up to about 30 gigahertz, it will go down and it will smear out. It will also get faster, okay? So it will move to higher frequencies, okay, as you dump ions inside it. But if you dump dipoles inside it, i.e. molecular components like proteins or glucose, it will once again go down and broaden out, but it will also become slower. It will shift to the lower frequencies. Big question, of course, is why? What actually happens? Well, without going too much into it, when you put in things like sugars inside blood, water sticks to sugar via hydrogen bonding, and basically this has a slowing effect. If you stick ions inside it, ions grab small amount of water or simply perturb or disturb water. That has actually a speeding up effect, and so we get these big changes. That is really crude, what I said. And if I said this in one of the conferences where I usually appear, I would probably be kicked off the stage. Okay? This is a little more complicated than that. It is actually a lot more complicated than that. There's also a matter of interchange between what you'd consider bulk water and the water that's trapped around ions. But it'll do for the moment. So let's have a good look at some examples. So here's some spectroscopy on salts ionic liquids. And this is, I'm not the first person to have done this. Far from it. This has been done for years. And in fact, this is images from a paper in 1987. Yeah, 1987 by Udo Katze, where he first looked at putting sodium inside. And you can see as he puts more sodium inside, this is pure water. And in those days, these measurements were extremely hard to do. It wasn't easy to get hold of a machine that could measure at 30 gigahertz in 1987. And as he puts the salt inside, you can see things move down. They get more broad, and they change their positions. Okay, simple ionic salts. Now, what's actually happening, of course, is something along this idea. And this is actually a very old picture. This is from 1999. And here you can see there's a sodium ion, and it's grabbed some water molecules around it, and they've stuck around it. That means there's not much water molecules left to become, if you like, relaxations, as we'd know. And this is a chlorine ion, and it seems to have grabbed, but it doesn't actually grab. It just simply bulges everything out of the way, and we'll talk about that in a minute as well. So what is that broadening? Why does it happen? I've warned you that I was going to throw some physics inside, and here it is. But I'll try and make this simple. Now, look at this. This is an idealization. I've got a bunch of ions, positive and negative ions inside there. And if I sum up from this origin point their positions multiplied by their charges, I'll get a figure, and it will be basically this vector. Okay? That's what it will be. Now, if I start shifting that ion, I'm going to shift that vector. It's going to move. So basically, if something moves inside, I get to change somehow the polarization vector, which of course changes the permittivity that I measure. Now, if this happens at equal steps, and you can take this function f to be this over here. If this happens all the time, and for simplicity, we'll make these like big fat ions so they can't move, and we'll just move that. If this happens in equal steps and at equal times, like that, then after a little bit of maths, it's not so difficult to get that, the Debye equation. And that's what the Debye equation means. Self-diffusion, famous Brownian motion, in other words, that you've all heard about. However, nature doesn't do that. Because who knows what this is going to encounter along the way? Maybe it's attached, maybe it's impossible, maybe there's a gap, a block of some form. In that case, if I introduce the idea that it may wait a little bit between jumps, and it may not jump the same distance each time, but less, more, then I need a whole new set of mathematics to describe that. And this maths was invented by a guy called Louisville, and coincidentally another guy called Raymond, way back, middle end of the 19th century, and it's called fractal derivatives. Basically, if I translate this horrible looking thing, okay, it says, you want to know how this is going to change over space, and you want to know how that's going to change over time. There's going to be sort of like a function to work on it, which will somehow describe you the waiting time that's going to take and the difference in steps, the distribution that's going to be inside there. Use that mathematics and you get the cold. So basically that's what that alpha is telling us. It's telling us, and if I can find out about it, that somehow there's waiting times involved, somehow the motion is not simple inside, and if I can probe that and I can find out why the motion is not simple inside, I found out an awful lot about the material. And we'll talk about what that can give us. So, summarize that. Anomalous diffusion, as I said beforehand, that's actually what that operator looks like. It's absolutely ugly, but that's what it is. Okay? It is really a continuous random walk, i.e. the number of times you can move in time are not going to be equal. They're going to be sometimes fast, sometimes slow, sometimes not at all. You're going to wait, whatever. That's going to work on a particular space function. We don't like space functions too much. So we'll average out all the space functions, because if we're measuring using a vector network analyzer, we're just measuring the whole sample. We can't see anything about space, just see about time. Do that, you're going to get this. If you can consider that microscopically, there's a whole bunch of things it's got to go over, yeah, to make that motion, it's impeded and whatever, that gives you an energy landscape. I won't talk about that. Put those things in together, and then you add one final moment. You say, look, this is a memory function. What it means, if I translate that, it says You want to know where this is going to go. You need to know where it's been, basically. And if where it's been has some self-similarity involved, and to picture that, think of this. Your bad-tempered, naughty little 5-year-old kid decides to climb a tree. If you're close up, you'll see him going from nearest branch to nearest branch. If you go far away, you won't see him going from nearest branch to nearest branch, but you will see him going from big branch to big branch, and eventually, if you go far enough away, you just see him going up a tree. I.e., the scale at which you looks the same picture seems to repeat itself time and time and time again. The scale seems to be the same. Nature loves this sort of stuff, and it appears that if you take that into consideration, that this will actually, this memory function, where it was, will tell you where it's going to be, involves that scaling according to the length and the time you look at, you're going to get this. And that alpha will then have a meaning. What it says n, the number of interactions it's going to make, is going to be pretty much constant according to the time window in which you look. Time window for us is the frequency. Change the frequency, it's going to look pretty much the same over certain scales. It's going to broaden out. So that's what it looks. So here's some of the measurements that I have actually made. This, as you can see, is at body temperature. These are sodium chloride solutions. And as we've changed the concentration, and you can see very low concentrations here, we can see this broadening happening. This is the real component. This is the negative, the imaginary component. This, in the real component, says there's another process happening. That's actually an artifact due to the probe itself. But over here we have DC conductivity. We'll talk a little bit about that. Okay, we can see things changing. So what, you say? Well, here's sodium chloride, potassium chloride, both important ions inside our body, for instance. Very important ions going inside the cells and coming outside the cells. They regulate ROS, yeah, reactive oxygen species, yeah, the homeostasis of our cells. Very important to know how they behave in water because that's where they are. Well, they look pretty much the same till you compare them. When you compare them, you see they actually behave very, very differently. Remember, the electric charge on a sodium ion is the same as the electric charge on a potassium ion, yet they behave very differently. Now, all this I can see by doing gigahertz spectroscopy. Now, there's a reason why. It's the sizes and the shape and the configuration of these ions, which is quite so important. Here you've got a chart. That's from that nice book I showed you earlier, by the way. That's the sodium ion, that's the potassium ion. The shaded area is the size of the area which will hold water molecules. Potassium ion doesn't hold water molecules to it at all. It disrupts everything. And you can actually see this behavior somewhere else. You can do it and see it by what's called neutron scattering. And here we can see the residency times. How long will water molecules stay in the immediate vicinity of those ions? Okay. Now, the difference between this and this is that this required a machine which approximately was $50,000 US. This required a machine which was approximately $20 million. Neutron scattering. You don't get that cheap. I.e., the information I can get here too. And that is rather significant if you think about the amount of research that you can do or the number of user facilities that there are for neutron scattering in Europe or in the world. So I pulled out all those parameters of those two particular ions. So what? Well, I can see the alpha. There's this they broadly look the same. That's the potassium, that's the sodium. And if I remind you about that particular equation I showed you saying the number of instances, in this case what it's actually telling you, I'm going to skip a lot of research now, it's actually talking about how water molecules will leave the immediate area of clustered water, bulk water, and come into the immediate area of hydration water around the ion itself. How many times is that going to happen? And is that actually the moderating factor? That's what is actually telling you these two particular details. That's an important thing that we need to know when we want to consider how one of those ions will go through an ionic channel through the membrane of a cell where it's actually got to do the job we want it to do to regulate that cell. So this is actually quite an important thing to know about. So yeah, how long will it keep water around it? That's what we're getting from here. There's a lot more information. I'm not going to go into it. I'm sure you're relieved. Let's look at something a little bit more simple, the DC conductivity. Now, DC conductivity is plotted for you here for these two ions, and they're very, very different. You can see that the potassium, it's actually much bigger than the sodium. Same electric charge. Well, DC conductivity is in fact related by the Ernst-Einstein equation to one, the diffusion coefficient, how fast can these things move through water, the charge obviously, and the concentration. Well, the concentrations are the same here, but I made sure they were the same. But of course, the diffusion coefficient for these two ions is very, very different. Now, that's lovely, but it doesn't work. As you can see, I don't get a linear relationship here. I get a power law when I actually do the work and plot it. Very unusual. I get a power law. Well, that's self-diffusion, how we would like nature to behave. However, nature does not behave that way. A power law, it is a badly behaved 5-year-old child, and so we actually need to this what's called fractal diffusion. We have to once again take into consideration the fact that there are motions, there are times to wait, etc., continuous random walker. And that's something quite new. People didn't actually realize that. That's going to be published very, very soon. So there you go. So that's what you can do with gigahertz spectroscopy. Really good stuff. Let's look at another one, aging of red blood cells. Once again, I stress we did not take the red blood cells from the students, although it was tempting. That's red blood cells. That's how they should look. That's what they look like after 42 days that they've been circulating around you. Now, our body gets rid of those. However, if you are particularly unfortunate in life and you happen to find yourself one day in hospital in need of a blood transfusion, you will get a bag of blood which you will hope has only been there for a few days, because the blood in the blood bank could be kept theoretically up to about 40 days. However, after about 14 days, it stops looking like that and looks an awful lot more like that. Because of this in the blood bank, they will throw the blood away after 14 days because they just can't take the risk. They can't puncture the bag and look into it. They can't do microscopy like this, take pictures of it, because then you're tainted. Wouldn't it be great if there's a way you could look at that and find and check if the blood was good, yes or no? Because it's really important. An old geezer like myself needs to get new blood. Someone young and fit can tolerate the old blood. Okay? So we decided to check. And here you've got an experiment that we were doing. This is blood in a blood bag, okay, donated to us from the Hadassah Hospital. We are actually measuring directly its dielectric permittivity, once again using an open-ended coaxial probe here, and we're doing this, the frequency region from about 100 megahertz up to about 50 gigahertz. Here we have basically a waveguide, and we're putting the same signal through a bag to compare between these two measurements. And this is the sort of thing we see. Now, we have a few techniques where we can actually take the measurement the permittivity would get from this probe and actually remove, by using mixture formulas, the saline solution that was outside these blood cells from the solution that's inside the blood cells, the cytoplasmic liquid. And that's actually what you're seeing here. Okay, that's what I've written down there. Now, down here, we're comparing between the fresh blood and blood after a little bit of time. And you can see that it's changing. That's the fresh blood. That's the blood after, I think after about 2 weeks. Gone down, shifted out, broadened out. Parameters that I can extract and use. Now, what do I get from that? Well, this is what I actually get. All the blood samples we had, round about 30 days after we got them, there was a dramatic change in where that peak frequency was, okay? And we could gauge this by actually taking samples, because of course we're not going to use this blood on people, so we can take blood out and actually look at what it looks like, and we could do that by looking at the elongation factor, which is basically looking at how these cells deformed. And we can see that it's matched to the elongation factor. That's the elongation factor, that's our signal. Okay, so we could see this is happening, and it's changing between the 35th and this. It's quite dramatic. Okay, look at all the parameters, and it's repeated in all the parameters. You can see basically there is a discontinuity in the broadening parameter. The blood is becoming old. The blood is becoming dangerous. The blood is now at a state where it is basically dead. And we can see that in the gigahertz spectroscopy of that same blood. So this is really applicable stuff, really useful stuff. Now, turns out you can also do this with nuclear magnetic resonance. And actually, that black line is nuclear magnetic resonance. And this is the broadening parameter that we've managed to calculate, or rather extract from our data. And they behave exactly the same way. How much more do I have? Well, I've got another 20-odd slides. I'll run. And here's the interesting thing. To do that NMR, you need $5 million. To do dielectric spectroscopy, you need $50,000. Big difference. Very big difference. Now, because I'm now minus 5 minutes and going on for minus 6 minutes and who knows, minus 10 minutes, I'm going to skip this part about polymers, also highly, highly interesting, but I will skip it. I'm also not going to leave any conclusion because I'm arrogant enough to think that the conclusion speaks for itself. That's the joy of being a professor. Arrogance is our middle name. Now, a quick plug. If you would like to know a little bit more about spectroscopy and what it is applicable for and what you can do with it, you are welcome to come and contact me. You can also contact Owen. He'll be happy to put you in contact with me as well. And I hope that you have stayed awake and enjoyed this talk.